Okay, the first step here is to determine the coordinates of any relative min or maximums of this curve, y equals x to the fourth minus 4x cubed. And the first step of this is going to be to determine the derivative, because whenever there's a relative min or max of some kind of curve, that happens when y prime equals 0, because the slope is naturally flat there. It's naturally a slope of 0. So the first step is to determine y prime and then set it equal to 0. Y prime is 4x cubed minus 12x squared. And then it's going to be easier to figure this out if we actually factor out common factors here. So we're going to factor out a 4x squared, which is going to leave an x minus 3. So then when is this equal to 0? This is equal to 0 when x equals 0 for this factor, and then when x equals 3 for this factor. So now we can make a table to analyze the sign of y prime around these places where x is 0, or when y prime is 0, because whenever y prime goes from positive to negative, meaning the function is increasing to decreasing, then we have a max. And if y prime goes from negative to positive, means the function is going from decreasing to increasing, which would be a min. So we should make a table split up by where this 0 is occurring. Okay, we have negative infinity to 0. That's one interval. And then we have 0 to 3. It's another interval. And then we have 3 to infinity. And we're going to talk about f prime and then use that to describe what's happening to f. So there's a couple ways to do this. One way is we can just look at f prime and see that it's a polynomial that has an odd degree and an even coefficient, which means its end behavior is going to be down up, which means it has to start negative and end positive. So f prime has to start negative and end positive. And then we can say, well, what's happening at x equals 0? At x equals 0, we have this 4x squared factor, and we've talked about how if the factor causing the 0 has an even degree or an even exponent, meaning an even multiplicity, then it causes a bounce, which means that we hit that x-axis and then bounce and keep going down. So it's negative and then it stays negative. And then we already know it switches positive because we filled that in already, but we can also say this factor has a multiplicity of 1, an odd multiplicity, which means there must be a sign change that occurs at x equals 3, so it goes negative to positive. But if you can't remember how to do that kind of reasoning, or if all else is failing, you can just plug in numbers from the interval. So plug in x equals -1, plug in x equals 1, and plug in x equals 4. I'm just picking numbers in those intervals. And if you plug in -1 to y prime, you should get a negative output. If you plug in +1 to y prime, you should get a negative output. And if you plug in x equals 4 to y prime, you should get a positive output. So if f prime's negative, that implies f must be decreasing. And then it bounces and keeps decreasing. And then it starts increasing at x equals 3, which means we have a maximum at x equals 3. X equals 3 is a max. We have to write this. If it's an FRQ, we have to write this justification. Because f prime switches from, not maximum, minimum. Oh my gosh, I am a mess. Okay, it's a minimum. X equals 3 is a minimum because f prime switches from negative to positive. Okay, but we're not done because the question doesn't ask for the x value, it asks for a coordinate. So we actually need to know the y value as well. So we need to come up here to the original curve and figure out the y value where this minimum happens. So we plug in x equals 3. Y equals 3 to the fourth minus 4 times 3 cubed. Y equals 81 is 3 to the fourth, minus 4 times 27 is going to give us 108. 4 times 3 cubed, 4 times 27. So then y equals -27. So our relative min actually occurs at 3, -27. So next it has to talk about concavity. So for concavity, we're going to have to use the function that tells us about concavity, which is the second derivative. So we get 12x squared minus 24x. And again, the concavity is going to switch where the second derivative is equal to 0. So it's going to be easiest to determine that if we can get rid of factor out common factors. So we'll factor out a 12x, and that's going to leave us x minus 12. So then we have zeros at x equals 0 and x equals 12 is where this is equal to 0. So just like before, we can make a table. We're going to go negative infinity to 0, 0 to 12, and 12 to infinity. And we're going to describe f double prime, which is going to tell us about the behavior of f of x. So f double prime is 12x squared. It's a quadratic, which means it has up, up, and behavior, which means it must start positive and end positive. And then the factor causing the 0 at x equals 0 has a multiplicity of 1, so that's a crossing 0, crosses positive to negative. And then x minus 12 is also a crossing 0, negative to positive. Again, if you're not comfortable with that reasoning, plug in x equals negative 1. Plug in x equals whatever you want between 0 and 12, let's just say x equals 1, and plug in x equals 13 to our double prime, and you should get a positive sign, a negative sign, and a positive sign. So that implies from negative infinity to 0, we are concave up. From 0 to 12, we are concave down. And then from 12 to infinity, we are concave up. So then the last thing is it asks for roots of this function, which is what again? It was so long ago, x to the fourth minus 4x cubed. Okay, so we have y equals x to the fourth minus 4x cubed. When is that equal to 0? Well, it's equal to 0. Let's find out by factoring out an x cubed. And then we have x minus 4 left over. So it's equal to 0 at x equals 0 and x equals 4. So if we sketch this, we can put a 0 at x equals 0 and x equals 1, 2, 3, 4. All right, what kind of polynomial is this? It's an end behavior of up, up. All right. And then the other thing we know is that there is an inflection point at x equals 0 and x equals 12, because that's where the concavity is shifting. Okay, honestly, I've redone this video once already, and I don't want to do it again. This should say x equals 2, and this should say x equals 2, and this should say x equals 2. Okay, so you may have noticed that early on, and I'm really sorry about that, but I messed this up once already, and I think that's an easy fix to just say that that happens at x equals 2 and not x equals 12. This should say x equals 2. Okay, you were probably so ready to tell me I made that mistake, but there it is. Okay, so maybe I'll redo this when I have time, but I just don't want to do it again. Okay, so the inflection points happen at x equals 0 and x equals 2, which makes way more sense. But that's why we sketch things, because you realize that it wouldn't make sense for the inflection point to happen at x equals 12. Okay, so because this multiplicity is to the third, we know that x equals 0 is going to be a shoulder, okay, because the multiplicity of that 0 is odd and also greater than 1. So we start up, and behavior is up. It comes and it shoulders through, and then it hits this minimum at x equals 3 and then comes up at x equals 4. Okay, so this minimum happens, we found out, at 3 comma negative 27. That's what we figured out earlier. Then we have our 0 at x equals 4. We have our 0 at x equals 0. There's also an inflection point at x equals 0. It goes from being concave up to concave down, concave up to concave down. And then around x equals 2, it goes from being concave down back to concave up, concave down back to concave up. So that's what this table tells us about the curve. Okay, this table tells us where it's increasing and decreasing. It starts by decreasing, it keeps decreasing, and then now it starts increasing, so it goes decreasing to increasing at that minimum. And then, yeah, that's it. That's the whole curve. We have the correct x-intercepts, correct concavity, and correct minimum.